Welcome, everyone. For today's prep, we're going to start to look at series. All right, so first of all, let's start with our definition here. So we have the definition for a series, and we'll look at it in a second. We're going to start, though, with a sequence. So let's start with, we'll call this our original sequence here. And let's just write out, we're saying it's the sequence AN from going from n equals 1 to infinity. Again, the starting index here doesn't really matter too much. So sometimes we start with 0. We might start with 2 or 3. But for this definition, we're going to start with n equals 1. And let's just write out the first few terms of our sequence. So our first term is A1, A2, A3, A4, and so on. All right. So that's our original sequence. So you can think of a sequence as like an ordered list. All right. What are we going to be doing with a series? Well, a series essentially is our attempt to take this infinite list and add up all the terms. So a series is an expression of the form A1 plus A2 plus A3 plus A4, and so on. We just try to take all of our terms in this list, this infinite list that goes on and on and on, and we try to add them all together. And as we'll see, sometimes you can do this, sometimes you can't. And that's going to be our main focus. When can you do it, and when does it not work? All right, so rather than writing out all these plus signs, a lot of times we use the more compact notation. We use this sigma notation. So sigma here, just you think of it as a fancy addition sign. So sigma AN, and then we have our starting index here, n equals 1, and then it goes up to infinity. And sometimes we shorten this up if the starting index is kind of understood, then we'll just say sigma AN. So this is what we're going to be using to denote our series. And again, it's essentially we're taking our infinite list and we're trying to add up all the terms in that list. So the intuitive definition, like I said, we're trying to add up all the terms. And sometimes you can do this. So if you can, and you actually get a result, so if that sum exists, then we say our series is convergent. And if you run into issues, or the sum doesn't exist, well, then we say the series is divergent. So the question is, how do we add up an infinite number of terms? And just to show you types of issues that we can run into, I want to look at a little example. This is kind of a fun one. We're going to prove that 1 is equal to 0. All right, so let's look a little example here, just to show you some of the, we have to be careful when we're talking about adding up an infinite number of things. So let's look at the series. We're going to go from n equals 0 here, and we're going to look at our negative 1 raised to the n. And this is going to be a divergent series. And we're going to see why. Actually, we'll look at this one a few different times. But let's use this series to prove that 1 is equal to 0. So we're going to write this. Let's write it out. Let's write out the first few terms of this series. So we're starting with n equals 0. So when n is equal to 0, negative 1 raised to the 0 power is going to be 1. So we're going to have 1. Then the next term is going to be negative 1. So we're going to add in negative 1. Then the next term is back to positive 1. So we're going to add in positive 1. And then the next term of our sequence that we're adding in is going to be negative 1. And let's see, let me get a few more of these just so we have some stuff to work with here. We'll have another plus 1, and let's do another negative 1. And this is a series, so this sum just keeps on going. We're trying to add up all these terms. And then we're going to do it again. So let's write down 2 copies of this. So 1 plus -1 plus 1 plus -1. So we're just writing out the terms of our sequence, and then we're attempting to add them all together. All right, so just 2 different versions of this. In the first version, let's group every 2 consecutive terms together. So let's add up the 1 plus -1. We get 0. Okay. Then let's go to the next pair there. 1 plus -1, we get 0. And then let's go to the next one. 1 plus -1, you get 0. So if you keep doing that over and over, it looks like this just keeps on going like this, and you would expect to get 0. Okay. So the sum of this -1 raised to the n sequence is 0. Well, now, take 2. Let's try this a different way, but we're just going to group the terms slightly different. So let's leave off this 1, and let's just go to the next. And we'll just kind of repeat that strategy. Let's add these 2 terms together. What do we get? We get 0. So we're still going to have that 1, but then we get 0. And then if we add these together, you get 0. And then this -1 will be paired up, so that'll give us 0, and we add it to its next term. And then it just repeats. So it looks like we get 1 in this case. So we have this series, and in one version, it looks like all the terms add up to 0. And by doing the arithmetic a slightly different way, we get 1 in the other case. So we've proved 0 is equal to 1. Obviously, that's not true. And where we're running into issues is an infinite sum like this. You can't always do it. And we'll see more of a proof of why this series is divergent later on. All right, but this kind of gives you an idea of some of the issues you can run into when you're trying to add up an infinite number of things. So adding up an infinite number of terms is not like regular addition. So sometimes we can do it, but sometimes we can't. And so we have to be very careful with this. Whenever we do anything with infinity, we have to be careful. So how are we actually going to do this here? Well, we're going to first add up a finite number of terms. So our finite number of terms, this is going to be regular addition. So this part's okay. Adding up a finite number of terms, perfectly good. That's just regular addition. How do we extend this, though, to infinity? Well, as anything with infinity, we end up computing a limit. So once we have the finite number of terms added up, we're going to watch what happens as we add up more and more of those terms. So we're going to calculate the limit as the number of terms that are getting added approaches infinity. All right, so how do we do this? Well, we do it with something called partial sums. So partial sums, these are the finite terms that we're adding together, essentially. All right, so when we have this infinite series, sigma an, from n equals 1 to infinity, we're going to calculate a brand new sequence. We're going to call this our sequence of partial sums. And the nth partial sum is we're adding up the terms in our sequence. So we're starting at our regular starting index number, but then we're stopping once we reach a certain point. Okay, so this is a finite sum here, this nth partial sum. So in class, we're going to come back and look at an example here for that -1 raised to the n series. But I want to look at a different one. So we're going to be forming a brand new sequence, the sequence of partial sums. So we're going to have our original sequence, kind of the original list that we're working with, and we're going to form this brand new sequence, And the terms in this sequence are going to be S1, S2, S3, and so on. And this is going to be our sequence of partial sums. So the first term in this sequence is just the first term of our original sequence. The second term, this is the sum. You can think of this, the way you can kind of read this notation is that this is the sum of the first two terms. So we're taking A1 and A2, the first two terms of our list, and adding them together. Then S3, this is like the sum of the first three terms. So we take the first three terms of our list and add them together. And then S4, the sum of the first four terms essentially is, well, we take the first four terms of our list and add them all together. So when we talk about series, there's going to be a lot of different sequences and series that we talk about. So it's helpful to keep in mind what's the original sequence, and what's the sequence of partial sums. So it doesn't hurt to write these out. So our original sequence, this is just our original list. So we have an, we're going from n equals 1 to infinity, and we can also just list out the terms. So it's a1, a2, a3, and so on. Okay, so that's our original sequence. Well, we're also forming now, we're going to attempt to add up all these terms. So to do this, we're going to form a new sequence, the sequence of partial sums. So we're going to give this a brand new name because this is going to be a new sequence. And so we'll call this Sn, and we're going from n equals 1 to infinity. And we could use S1, S2, S3, and so on. But essentially what we're doing is the very first term of this sequence is just the first term of our original sequence. And then the second term of this sequence is the sum of the first two terms. So it's going to be A1 plus A2. And then, so we've got our first term, then we've got our second term, and now let's look at what the third term would be. So the third term of this new sequence, we're going to add up the first three terms. So it'll be A1 plus A2 plus A3. And then we just repeat this over and over again, adding up more and more of the terms. And the idea with our series then is we're going to try to calculate the limit of this series, this brand new, or the limit of this brand new sequence. All right, but first, let's just try an example where we actually calculate a few partial sums. So let's look at this example. So we have a series written out. So the first term is 1 over 3, and then we're adding in 1 over 9, then we're adding in 1 over 27, and then we're adding in 1 over 81. And again, let's just keep in mind, what is the original sequence here? So this is not a sequence. This is a series. We're just adding up an infinite number of terms. So our original sequence, and we have the formula for our general term here. So this sequence is going to be 1 over 3 to the n. And our starting index here, if that's our formula, n equals 1 is giving us that first term. So it's going to start at n equals 1 and go to infinity. So our original sequence is just this list, 1 over 3, comma 1 over 9, comma 1 over 27, 1 over 81, and so on. So that's our original sequence, and it's just the terms listed out. So what we're trying to do with this expression, this is called the series. Where we're taking our infinite list and we're trying to add up all those terms. Well, the idea is how we're actually going to do that is with our sequence of partial sums. So we're going to get a brand new sequence here. And we want to write out what the first few terms are. So let's start with S1. We're going to figure out S1. And we're going to we'll write it out. All right, so let's start with S1. So what would be S1? Well, this is the sum of the first term. So it's just the first term. So we go to our list, it's just the first term, so 1/3. All right, so then S2. What would S2 be? Well, it's the sum of the first two terms. So 1/3 plus 1/9. 1/9. Okay. Then S3. What would be S3? Well, it's the sum of the first three terms. So 1/3 plus 1/9 plus 1/27. And let's get one more, S4. We want the first four terms. So we need S4 then. All right, so what do we do for S4? Well, it's the sum of the first four terms. So 1, 2, 3, 4, we add all those together. So 1/3 plus 1/9 plus 1/27 plus 1/81. And so our sequence of partial sums is going to be a brand new sequence. We have our original sequence, which is just the original list. We have our series, which is where we're trying to add up an infinite number of items. And then we have our sequence of partial sums. So these are going to be the terms we found here. So the first term of this brand new sequence is going to be 1/3. And then the second term, and I guess we could probably get common denominators here. So this would be 4/9 if we want. So the second term of this sequence would be 4/9. And then next term would be, if we get a common denominator, would be 13/27. So that's going to be the next term of our sequence of partial sums. And then if we do the same thing here, 27 plus 9 is 36, plus 3 is 39, plus 1 is 40. So this would be 40/81. And that's going to be our last term, 40/81. All right. So we've got our original sequence, and then we've got this brand new sequence of partial sums. And this is what we're going to be investigating. So right now, I just want you to kind of be able to practice writing out the original sequence and then the sequence of partial sums. So we'll see you then. Bye-bye.